Mic on? Is it on? Yeah. Okay, let's get started. Cold enough for you? Yeah? For how many of you is this your first Iowa winter? Any first timers? No? Okay, so you're used to it. All right. Come on. I hate to think I have to stand here and use the podium, but I might have to. Okay, so a couple of things that I want to cover before we get started. Every lecture, I'll always have announcements at the beginning of lecture. I've made changes to the website. Do you guys look at Icon every day? So you know that there's like this running commentary on the home page. When you get there, at the top will always be the latest announcements. So I'll put things like reading assignments on there, and I'll also put them on the calendar. And I have put instructions for how you can incorporate the class calendar in your Google Calendar or whatever you use. You probably know how to do this, but the instructions are there. You had Lab 0 yesterday. How many of you were successful in installing Python? Good, all right. If there are any problems, post to Piazza and we'll help you out. I saw about 110 of you uploaded Lab 0. It's not worth anything, but it's useful for you to sort of practice the upload so that when you get your first question of the day and you get to the real labs, you've already done that once. And by mistake, by my fault, I had the lab close at midnight last night, meaning you couldn't upload stuff. So I've reopened it until midnight tomorrow night. So if you didn't get a chance to practice uploading a Python file to Icon, you can still practice. Okay, so there's that. I'll probably post the first question of the day on Friday. No, it's not a slow start, but we have things to talk about first. But now that we have at least some little bit of Python, you should be able to start writing a few function definitions. So I'll start posting questions of the day on Friday. And on those, if I post it on Friday, it will be due on Monday. If I post it on Monday, it'll be due on Wednesday. And usually I have them due in the morning right before class. So when we come to class, the first thing we do is look at the solution of the question of the day. So it'll be the first slide every time we have one due. I have some reading assignments. This is a shorthand I use. This is the Think Python book. This is the Python for Everyone book. You've all found the book sources online at Icon, right? It's PDFs. When it's or, it's because these books come from the same original source. They're two different people's takes on an open source textbook. So I don't recommend one over the other necessarily, but I will point out that the chapters diverge. They're not in the same order. So whenever I have an or, you're welcome to read either one, but be aware the chapter numbers are different. And when I give you an assignment like today, I expect you to read it by the next lecture, so by Friday. So you leave today, you can go home and read chapters 2 and 3, or 2 and 4 if you read from Python for Everyone. Okay. So let's review where we were last time. We just started talking about built-in data types, and we had, in fact, started talking about integers. And I also described that every built-in data type comes with a set of operations that are used on that type. So in integers, there's things like plus and minus and so on. And then I also described these functions, like max and min, that are defined on that data type. So we have a max function, takes 2 arguments. It returns as its value when evaluated the larger of those 2 arguments. And the thing to remember here is that the function invocation, in other words, when I write min minus 1, 1 plus max minus 1, 1, this expression, this is of course an operator on numbers, integers in this case. And each one of these sub-expressions stands in for an integer. It says, I don't know what the value is here, but whatever this function returns when evaluated, that will be the number that you add to the other number. So the function invocation, this, stands in for a value which is the value that function returns. So how does all this work? So the idea here is that when we say we're programming in Python, by and large what we're doing, not all the time, by and large what we're doing is we're writing new functions that extend the language. Those functions work on data types that are either built in, like these, or that we've defined ourselves. So here's what a function definition looks like in Python. And this is the kind of thing you'll be writing on every question of the day and on every exam and so on. So there's a keyword here that's used to introduce a function definition. The keyword is def, and a function definition looks largely like this. So it starts with the keyword def. You type that right to the prompt or into your file if you're typing into a file. There's a name of the function that you get to pick. I wouldn't pick max or min because those already exist. But you can pick any name you like that's, my max, my min, whatever you want. So this is the name of the function by which it will be invoked. And then we have a list of something called formal parameters. It's a list because they're enclosed in parentheses, round parentheses, with commas separating them. Now, in Python, unlike some other languages, the type of parentheses you use are semantically meaningful. They carry meaning. When I say parentheses, I mean the rounded ones. If I mean curly brackets, I'll say curly brackets. And the other type of parentheses are the square brackets, which I'll just call brackets. So here we have the parentheses containing the parameter list, followed by a colon sign. So that's really important. People forget this and it doesn't work. After the top of this function definition, this is called the signature of the function, is the name and the parameters. We have a series of statements in Python. All of these are indented below the definition by one tab. So for those of you who are used to writing languages like Java, where you use curly brackets to give structure to code, Python doesn't do that. If you look at Python code, it looks very different from Java or JavaScript or C or C++. There's a complete absence of curly brackets except when they have meaning. Instead, the structure of Python is given by the indentation. Now, some people don't like that. Indents are hard to see. Are those indents or are those couple of spaces? But indentation matters. And when you have something that's not being parsed by Python, when you type something to Python and it breaks, one thing you want to check always is that the indentation makes sense. So this is the general form of a function definition. Typically, a function will end with a return statement and then a list of values that you want to return, presumably the results of what you've calculated. That's not always true, but it is often true. All right, so remember, without those curly brackets that you see in other languages or any other syntactic cues, the indentation matters. It carries meaning. They're semantically relevant. Also, these return values are the things that stand in for the result of the function. So if I were defining the max function, and I had two parameters, column x and y, I would be determining which one was larger, and I would be returning one or the other here. Okay? Sorry. Okay, so the function definition starts with the def keyword. Here's an example. We have a list of parameters. There can be as many or as few here. It is possible to have a function that takes no parameters. Not very useful, but it's possible. So function name is the name of the new function, and these are the names of what are called the formal parameters, or just parameters. The function is defined with this is called the function signature. Atom up xy tells me what the function is invoked as. It tells me everything I need to know about how to use the function, except for what the function returns. When you write a homework assignment, or when you get a question of the day, I will always provide you, at least initially, like for most of the semester, I will provide you a series of function signatures. So question of the day will look like, here's what a function, I'd like you to define a function that does this, and there's a description of the function, and then there will be a function signature, and you have to complete that function. That's typically what I'll ask. And these formal parameters, x and y, they can have any name you like. You can give names to your formal parameters that you choose. It is useful if you make those names, and actually will be required, that you choose names that make sense. So x and y here, I'm defining my new function called AtomUp. I have two parameters, x and y. Those are crummy parameter names, right? Because they don't really tell me anything about what these are. A better parameter name might be n1 and n2, perhaps, to indicate that these are two numbers. But in the sense of a simple function like AtomUp, there's often not a lot you can say about those formal parameters, so x and y will do. All right, so here's my AtomUp function. It has one line in it. There's an indentation here that you can't see, but it's obvious from the context. The whole function is simply a return statement that returns the value of x plus y. So call AtomUp. I give it two numbers. I get back as its value the sum of those two numbers. Simplest possible thing I can do. So some more terminology. You already know that this is the function signature, that x and y are formal parameters. So when I invoke AtomUp, in other words, when I type it to Python or use it in another function, the things that I pass to x and y are called the arguments to AtomUp. So these are the values that I'm going to evaluate and then pass those into the function, mapping them one-to-one to each of the formal parameters. So let's see what those terms actually mean. So here's my invocation of Python. The little caret there shows that I'm in an interactive Python session. I'm going to invoke my function by giving the name of the function and then a list of arguments. Notice how the invocation of the function looks exactly like the signature, except instead of formal parameters, I actually have arguments I want to use. Now those arguments are, in this case, numbers, but they have to be evaluated. So the way this works is, when I type this to Python, it says, oh, I've got an invocation of the AtomUp function. I know what that is. It takes two formal parameters. It looks at the invocation to see the arguments. It says, the first argument is 3. Let me evaluate that. The value of 3 is 3. So that value is going to be mapped onto the first formal parameter. So I'm going to use x as if it were 3 in the evaluation of the function. Similar process for 4. I evaluated, I mapped that value onto the formal parameter y. And now when I say x plus y, I'm really saying 3 plus 4. I evaluate that, the value of that is 7, and that's what I return from the function invocation. And because this is the read eval print loop, the value that's returned from that invocation is printed to the user before we go on and get the next prompt. So the whole process here for simple function evaluation is actually pretty complicated, right? It starts at the prompt with figuring out, do I know this function? And if I know this function, can I map the arguments, or better yet, the evaluated versions of the arguments, one-to-one to the formal parameters? And if I can do that, then I can evaluate the body of the function with those argument values as the parameter values. And I get a value that I return, which then is passed back to the Python REPL, which prints it, that's the P, and then it goes back in the loop. I didn't show you the prompt here, but the next prompt comes up right away. All right, is that clear to everybody? Now, this is like pretty detailed. It doesn't really matter. You sort of get the gist of it by seeing it once. It's a lot like using a calculator. But I do think it's important to know these terms, in the sense that it's always better to have precise language when you talk about something like this, carefully. The idea that the arguments, for example, are evaluated and mapped onto the parameters, that's interesting, an interesting concept. In some languages, this kind of mapping happens in one way. In other languages, technically it happens in a very different way. And those differences turn out to be really relevant. Not now, but they will be later. So it's important to set up good habits about terminology early. So let's see how this can possibly break. Well, first of all, I had two formal parameters, so I gave it two arguments. If I do things differently, they might break. So here I have AtomUp 3. Python looks at this and says, I know this function. I've got a parameter, an argument here, which I can evaluate and map to the first formal parameter, but I don't have anything for that second formal parameter. And so Python will complain. And when Python complains, it tries to give you some information. Now, sometimes that information isn't very helpful, but it helps to know what we're seeing here. So the first thing we see here is because we didn't get a value, we can sort of decide that, yeah, there's probably an error here. At the very end, before the next prompt, you'll see information about the error. Typically, what you'll see is the kind of error it is. This is a type error. I'll explain why it's a type error in a minute. And then a statement that's trying to give you a clue. It says here, the atom up function is missing one required positional argument, another word for a formal parameter. Or, sorry, another word for the argument that maps onto the formal parameter called y. So this statement, along with our definition of atom up, is enough to sort of give you a hint that we're missing something. Right before that, this stuff, this is important when you have a larger, more complicated system. When you are using many functions that invoke each other, for example, if Python gives you an error, it's helpful for you to know in your model of how these functions are evaluating, it's helpful to know where it breaks. And this is what this information is giving. It's saying, look, you've invoked this from the shell, and it broke when I got to this step. Now, that doesn't mean much when this step is the only step you've got. But when the steps are many, it means a lot. So reading an error message, I always start from the end to see if it's something that I can immediately recognize. And if not, I look to see where it actually broke down. And I use that as a clue. What do you think happens here? Anybody? Too many, right? You got one too many. So sort of the analog of having one too few. I get the same idea, the same type of error, but now I have a different error message. Now, why is this a type error? We all know what types are. We said integers were a type. They're data types. And here I don't see how having 2 arguments or 3 arguments instead of 2 is a typing error. And the answer is, it's not because you have too many types, it's because the function itself is a piece of data. And it has a type. And the type of the function is, I get 2 parameters, but you're given it 3. So you're breaking the definition, the typing definition of that function definition. To some degree at the beginning, as you start with Python, this is less useful. This statement is the most useful. So focus on what it's telling you, less on the type of error it's declaring. All right. Now, there's a lot of excitement in CS1. Can't you feel it in the room? Maybe not. You kind of want to get started writing stuff and doing cool stuff, right? But in fact, at the very beginning, it's baby steps. And we do take things, in a way, at the start of this class, excruciatingly slowly. Sometimes it's annoying because you say, good Lord, we've just spent a week on integers. Is this ever going to get any better? But the answer is that sometimes the devil's in the really little details. And I want to show you why. So we discussed up to now just integer types and some simple integer operations. And while these were pretty straightforward, with the exception of the integer divide and modulus, everything was pretty much okay. But there's actually a lot going on with that integer divide and modulus, which we don't really think about. How many of you went home and said, wow, what he told us about integer divide and modulus is really not well defined. It's inconsistent. Did anybody even have that thought? I guarantee you the answer is no. But let's look at it a little bit more carefully. So if I write A integer divide B, I am writing an operation that returns a quotient. And that quotient, in a sense, is how many copies of B fit into A. These are whole numbers. These are integers. There's no fraction. Q is an integer. And then the remainder is R, which is what's left over. In other words, this whole thing of integer divide and modulus, it comes from this equation. where I have some quotient times the base plus r equals the number I'm starting with. So for example, 7 integer divide 3 is 2, because 2 times 3 is 6. So 2 times 3 is 6, plus a remainder of 1 makes 7. Right? That seems pretty straightforward. But it's complicated. So here our example is 5 integer divide 4 is 1, 5 remainder 4, so 5 modulo 4 is 1, because 4 times 1, sorry, this should be 1 times 4, you get it, plus 1 is 5. But it's key to understand here that there are a lot of solutions to this equation here that work. This one of saying that 5 integer divide 4 is 1 is one of many solutions that work. I could say 5 integer divide 4 is 2, because 2 times 4 is 8, but with the remainder of minus 3, I still get the 5 I started with. I could make this 3 and have a remainder of minus 7. I could actually have this be a negative number and have a large positive remainder. So what is it that's special about this solution that we prefer over the infinitely many solutions that are possible? And the answer is, and probably what you don't even think about and assumed, is that in the case where a and b are greater than 0, meaning both the base and the original number are larger than 0, we want r to be between 0 and b. In other words, we implicitly assume when we're doing integer divide, we want to know the maximum number of copies of b that fit into the original number a. So go back to grade school where you drew number lines. Do they still do that? You do number lines in grade school? You think of 0 here, and a over here, and b is a smaller integer, and you want to fit as many of those in and leave a remainder such that the remainder is between 0 and b. That's what makes that solution special. There's this assumption that that's the right solution to get. And one thing about computers is they have to be consistent. Languages too. And when you write an operation like integer divide, you want to make sure that every time you use that, it gives you a consistent answer. In other words, it always gives me, 5 integer divide 4 is 1 with remainder of 1, and doesn't give me this solution at random. Because then I would have something that's not deterministic, it's not useful. So it's always got to give me the same solution. Of course, the problem is, when one of these, a and b, is negative, then everything goes to hell. Sorry, goes to pot. Should minus 5 integer divide 4 be minus 2 with the remainder of positive 3, or should minus 4 integer divide 4 be minus 1 and a remainder of minus 1? What's the right answer? Up here, the right answer was kind of intuitively obvious because we think of positive numbers, when we think about modulus, it all sort of works out. Nobody blinked when I said, as many b's as you can fit into a. You all said, yeah, that's right, it's obvious. But it's much less obvious in the negative number world, right? What is the right thing to do? And here, stuff that you don't expect happens. So in Python, the remainder and the base, the remainder and the original base share a sign, always. That's the rule. What does that mean? That means that negative 5 integer divide 4 is actually minus 2, because 4 times minus 2 is minus 8, and then the remainder is positive 3. So think about it. When I switch the sign on the 5, it changes the absolute value of that result. It changes it from 1, so in the positive sense, it's 5 integer divide 4 is 1. Negative 5 integer divide 4 is minus 2. So that's weird. But that's the way it is in Python. And unfortunately, in other languages, it's the opposite. So we take things slowly at the beginning in this class because there's a lot of murky details that only later, much, much later, will you be grateful that Python works this way and not the way you sort of intuitively think it ought to work. These subtle issues in the design of the language have a habit of sort of popping up later and really, really making you suffer if you're not aware that not everything is immediately as you assume it seems. So this is a cautionary tale. Pay attention to the details, even on simple things like data types. Okay. Well, I think we've beaten integers pretty much to death. We'll go faster now. Next one we're going to look at is floating point numbers. They're a little bit easier, a little more obvious for you, perhaps. Floating point numbers look like integers, except they have this. They have a decimal point. The values evaluate directly, but the input formats are a little bit more flexible than those for integers. So remember, what is an integer input form? Plus or minus, optional. Digits from 0 to 9, as many as you like. That's it. Floating point numbers is the same, plus you have the added necessity of having a decimal point. But there are other input formats for decimals too. I can write decimals or floating point numbers in scientific notation. This is 235. The e is the exponent, so 235 times 10 to the 8th. And when I type that, so notice here, there could be a plus or minus here. There can be a plus or minus for the exponent. But there's this e here that's important. And when I type that, Python evaluates this and returns a representation of a floating point number, which is in fact 235 times 10 to the 8th if you count the zeros. If that number is larger, and by the way, the e can be upper or lowercase, here's a very large negative number with a very larger negative exponent. Python changes its representation. It evaluates it. It builds the internal representation of the floating point number and then produces a printed version for you, which now comes out not like a floating point number here, but it also comes out in scientific notation because it's too large for you to want to look at. Now that's kind of silly because you saw really big integers. Python has no problem printing out 1,000,000 digits for an integer. But when the floating point numbers get large, the precision is not all that, internal precision is not all that great, so it will resort to using this shorthand notation to print out a number. But the same general idea applies from integers. You type a representation of the number you mean, Python builds an internal representation of the number you mean, and echoes how he thinks you should have written it, or it thinks you should have written it, which may not match the way you input it. But it's this underlying, it's the same number. Minus 9999. This is not a floating point number, it's integer, so we get an integer back. If I add the decimal point, don't need anything after it, just the decimal point, that tells Python it's a floating point number. Okay, operations on floating point numbers are exactly what you would expect. They look just like integer operations, except that when there are floating point numbers involved, the result's a floating point number. When I use division on floating point numbers, I use the regular division sign, not the double slash, and I get back a floating point number. And these numbers, they have the same order of operations. The parentheses here are just grouping like in algebra. That's their significance. And I get back a decimal. Now, one thing you'll have noticed looking at this is that there's this sense that when you mix integer and floating point numbers, Python could do one of two things. It could throw an error saying, I don't know how to add integer and floating point numbers. But that would be really stupid. So what Python does is it changes the type of any integer that is involved in an operation with a floating point number. It casts that type to floating point. So in other words, in this very first one here, I have an integer times a floating point. Internally, there's an integer representation of 34 and a floating point representation of 1.2. You can't multiply those. They're incompatible. They have to be the same. So Python silently converts this 34 into a floating point number, does the operation which results in a floating point number. So when you mix operations with integers and floats, they become floating point results. Now, You know, in the spirit of our little foray in modular arithmetic, some things about floating point numbers will surprise you as well. Let's say I have 3, 0.1, 0.1, 0.1 added together. What's the answer? What is the value it should return here? Will it be integer or floating point? Be floating point. And what do you think it is? Anybody? 0.3. Python returns this really weird number. Why does it return 0.3 with a bunch of zeros and a 4? Well, we've all had that experience, certainly in grade school, when you first divided the number 1 by 3, and the teacher told you that the value is an infinitely long decimal, 0.333, continuing, right? They taught you to put a little bar over it, or approximate it, you know, or just truncate the representation. Those issues that you encountered in K-12 are due to the fact that the decimal system is bad at representing some numbers. I'm not talking about irrational numbers. I'm not talking about pi. I'm talking about numbers like 1/3. It's hard to represent in decimal. Computers, though, are binary. They're not decimal machines. They're binary machines. And there are the same kind of representational issues in binary, but they don't occur in the same place. So right here, we've made one occur. It turns out that 0.1 can't be represented in binary without that same representation that we have for error we have for 1/3 in decimal. So in decimal, it's 1/3. In binary, it's 1/10 is hard to represent. So you may have operations that you expect to act in a certain way, and your expectations are set up by what you know about math, arithmetic, and also what you've encountered in a largely decimal world. And every once in a while, those assumptions that you make will be questioned because we're not in a decimal world anymore. Python's working very hard to make it look like we are, but underlying this, we're dealing with representations of numbers that are binary, and sometimes that pops up. So just be aware. All right, let's write some Python. Write a function called kilograms to pounds that converts a value given in kilograms into its value in pounds. I'll spare you looking it up. The conversion factor is 2.2 pounds per kilogram. There's my function definition typed to the Python prompt. Def kilogram to pound, one formal parameter w, colon, to introduce the function definition. And I hit enter, and then I hit tab to move it over. And I type return w times 2.2, simple function. Python provides a new prompt. Notice that when I typed this function definition, Python didn't give me any value back. So I typed a statement to Python that said, extend yourself to know what kilogram to pound function is, and Python was silent about it. It just changed the internal state of Python. But now the prompt says I can type something else, so I'll try my function. Kilograms to pound 1, integer 1. The answer I get, of course, is 2.2, because 1 kilogram is 2.2 pounds. So far, so good. Kilogram to 10, 22 pounds. Notice that even though this was an integer, this is a floating point number. Why? Anyone? Yeah? Okay, so that's the stinker in the function definition, right? There's a floating point number here. So w, which could be either integer or floating point, is going to be floating point because it's multiplied in a mixed mode operation with a floating point number. But of course, if it's a floating point number, I'll get still a floating point number. All right, so here we go. The value returned is always a floating point number, regardless of whether w is an integer or a float. Now, those of you who write C code or something else, notice that the parameter w is not typed. When I defined this function, I didn't have to say that the input argument is always a floating point number. I didn't tell you what the input argument is. It could be integer, it could be floating, and in fact, Python doesn't care. It allows you to use either one. So this is different than what you have in other languages. And we talked about this the very first day. I said Python is type flexible, meaning that variables, or parameters in this case, don't need to be declared to be of a certain type. Is everybody okay with this? Yeah, you bored yet? My daughters would say, you survived more than a half hour with me. You're doing really well. Let's do some more. New function, pounds to kilogram. Same idea, except we're going to do things the other way around. W divided by 2.2 is the value we return, so anything I give you returns a floating point number that's the result of that division, just like you'd expect. Remember I told you that when I evaluate a function invocation, I map the arguments onto the formal parameters. And the arguments themselves have to be evaluated. So in this thing, I encounter pounds to kilogram. The argument is this kilogram to pounds of 1. I have to evaluate this function invocation. What does this return? The internal one? So 1 kilogram is how many pounds? 2.2, right? So this will return 2.2. We saw this on a previous slide. And that 2.2 then becomes the argument to the pound to kilogram function. So this is an identity, right? We're going to evaluate one conversion, and then we're going to convert it back. And so what we should get back is, of course, 1. And 1 will be floating point, because even though this was an integer, the return value here is 2.2, which is float, which is then divided by 2.2 here to give me a 1.0. All right? Notice that this definition and this definition both use the same formal parameter w. But the w in one function is different from the w in the other function. They have different values. They're completely independent. We say that the scope of this formal parameter, w, is only meaningful inside the definition of that function. And likewise, the w formal parameter inside this function, which you saw on the previous page, that is a different w. So start to sort of question why I use variable names like w and so on, and what they mean, and how long they have value, and how long they persist. And this example here, very short example, sort of should bring some of those questions to mind. Questions, anybody? No? All right, I can do it backwards, still get 1. All right, so that's floating point numbers. Told you we'd go faster. I'm not going to talk about complex numbers. You want to read about those, they're in the book. If not, there's an excellent Python documentation website from the Python project. I'll post the URL on the website. You should all bookmark that URL for questions about how to use built-in Python functions or types. It's the place to go. So I'll provide that at some point. Look at the next type. We're going to move from numeric types to logical types. We'll start with the logical types. They're called Booleans. They're called Booleans because they're named after a 19th century British clergyman and philosopher and logician, a guy named George Boole. Not memorable except for his obsession with logic. And so we have he was, mathematical somebody. Anyway, so George Boole, that's why we call them Booleans. Booleans are logical values. There are 2 values in the Boolean system, true and false. True evaluates always to true. False evaluates always to false. Notice that the true is uppercase. A lowercase true is an error. It gives me an error, different type of error, a name error that says, I don't know what true is. I've never seen lowercase true. But I sure know what uppercase true is, and I know what uppercase false is. So in Booleans, in integers you have infinitely many values of that type. In Booleans you have 2, true and false. That's all you get. Like, however, integers and floating points, they have operations defined on those values. The operations are the logical operations, many of them. We'll see 3 of them. The logical operations are negation, conjunction and disjunction, or not, and or. So here's an example of an operation, or, applied to 2 Boolean values. OR expects Boolean values as its operands. So the value of true or false is, anybody want to guess? It's true, right? So like in grade school or in junior high or whatever, you know, when they say if it is raining, then there are clouds, that kind of junk that you did in grade school from basic logic, those rules apply here too. A disjunction, a logical expression with an OR connector is true if and only if one or the other of the operands is true. Here, the first operand is true, case closed. Not false. Not is a unary operator, takes one operand. A disjunction OR takes two. OR is kind of like plus or minus, or two operands. Negation only has one. It's a lot like a minus sign. So not false takes false and turns it into resounding response, true, right? And takes true and returns it into false. The last operation, and, false and true, and an expression with an and is true if and only if both of its operands are true. The first operand is false, so it doesn't matter what the second operand is. So we're going to say this is false. And I can string these together. True and not false and true. I can do this so much that parentheses for grouping can be very helpful for us because these things are hard to read sometimes. Python doesn't need them. Python will resolve this expression using internal rules of operator precedence. The internal rules of operator precedence group the not tightest of all. So this statement becomes true and true and true. And true and true is true. That first result, and true is true. So the whole thing will be, of course, true. Questions? Wow, that's it. Oh, yes, go ahead. Danielle, right? Daryl. Okay.
So on the and statement, if it was flipped, if it was true and false, it would still be false.
So if you have true and false, it would be false because the true part is true, but and requires both of its operands to be true. And as long as you get one false in there, you know, game over. Good question. Anybody else? We're cooking with gas. All right. Little digression. We now have, yes, go ahead.
What would happen if you had true or true?
So true or true, or is disjunction. It's an operand with two operators. It is true if and only if at least one is true. So as soon as you have true or, you're done. Doesn't matter what the second one is, because the whole thing is true. All right, good. By the way, I encourage you, somebody asked on Piazza, how do we study for this class? That kind of question, the easiest way to do that, open up Python, start typing. You know, you have trues and falses, you know the three connectors, start typing expressions. And the minute you see something that is surprising to you, like that 0.1, 0.1, 0.1 added together giving you 0.3 something else, that's what you post to Piazza. Why does this happen? If we get enough people doing this, there'll be a community of questions, and you feel free to answer each other's questions, or one of us will always answer. And that way you sort of get to see, you know, Python is an experience, and you need to sort of experience it, which is why you'll get so many questions of the day. All right, sitting at the Python prompt, I can ask Python, what is this thing? So we've seen so far integer and floating point numbers and Booleans. There are functions that can tell us what that thing is. So for example, a 3 is an integer. Python will tell us, will return this funny construct that says that the 3 is part of class int. Int is Python's way of saying integer. Now, we'll ignore for now the angle brackets, yet another type of bracket that has meaning in Python. We'll ignore this word class. We'll ignore the fact that it has funny quote marks. Just focusing in on this, it tells us that this is an integer. Similarly, for a floating point number, I'll get a class float. And for false, I'll get a class bool. So I have a way of testing whether something is of some type. And this is important. Why? Because Python variables are not typed. That means the W in our definitions before can be sometimes an integer and sometimes a floating point. And sometimes you really want to know which it is. What is its value and what type is it? So I could have as easily said type W in my function and it would have told me, you just got past an integer. Or you just got past a floating point number. So we use this type function to determine what it is I'm looking at, because sometimes I may want to do different things with different types of arguments. So helpful use of function type. Again, those little hidden little things, don't expect that type conversions, I haven't talked about type conversions, this was in the wrong slide. Let's go on and then sorry. That got added to the wrong slide. We'll come back to that. My fault, my bad. So just like I can find out what something is, I can also convert something from one type to the other. We've seen that that's happened before magically. When I try to add an integer and a floating point number, the integer was converted. But I can do it explicitly using functions that are named after those types that I got from the type. Remember that type statement I just showed you on the flawed slide. So I can take a false and Boolean and convert it to an integer, and I get this number 0, which is weird. So somehow, somewhere inside Python, if I convert false to an integer, I'm going to get a value 0. What happens when I convert an integer 1 to a Boolean? Well, surprisingly, I get the value true. So having seen this much, you might form the hypothesis that internally, a Boolean false, and an integer 0 are represented the same way. And a Boolean true and an integer 1 are represented the same way. So that might be your working hypothesis. If it isn't, it should be, but that might be your hypothesis. So let's keep exploring. What happens when I take an integer of 17.0? Well, the obvious thing happens. What happens when I take an operation on integers and upconvert it to floats? Get the obvious thing. What happens when I say float of not false? Well, not false is the argument to this function. I have to evaluate this expression. Not false is true. If I convert a true to a float, what do you think we get? It's true. 1.0. So all of this looks pretty good. However, this statement should have been on the next slide. Don't expect type conversions to be symmetric. So for example, bool 2 evaluates to true, just like bool 1. But int true evaluates to 1 always. So if I start with a 2 and convert it to a Boolean, and then convert it back to an integer, I get a different number. When I convert something into a Boolean, I get down to 2 values only. And this example, and what we've seen so far, should point out that a 0 past a bool will give you a false, but only a 0 will give you a false. Any other value, a Boolean will take as true. So bool of 0.1 is going to be true, bool of 0 is going to be false, bool of 1,642 is going to be true, always. It's not 0. Only 0 and 0, 0 will convert from number to Boolean and give you false. Anything else will give you true. Unfortunately, if I try to go back from true, I don't know what that original number was anymore. So I'm going to cast it back and give you always a 1. So this statement is meant to go on the next slide and remind you that while these conversions look like they are straightforward and obvious, you are converting one set of representations, which may be infinitely large, like floating points or integers, to another, which only has countably few values. Information will be lost going one way or the other. Yes?
So if you had converted a number in
Yeah.
And then you did the same operation again, you did true to an integer, like so maybe once it's already established what the number was before.
So if I have a number, 1700, and I convert it to Boolean, I'll get true because 1700 is not 0. And whenever I convert 1700 to Boolean, I will always get true. Now, if your question is, if I have a variable whose value is 1700 and I convert that to bool, that conversion will return true, but it won't actually change my variable. We'll do that a little bit later when we talk about variables. I don't know if that was exactly your question. If not, post. We're out of time, so post to Piazza and I'll answer it more carefully. All right, we'll see you all on Friday. Don't forget to read chapters 2 and 3.